How's it going, guys? In this video we're going to go over some thermochemistry basics, and we're going to calculate heat through phase changes. And basically a bunch of thermochemistry concepts can be simplified into a basic chart, and if you can memorize the chart, the rest just is calculations. So I think it's worth going through the chart, so we're just going to go over that really quick. So first of all, kind of have just the basic y-axis and an x-axis, and on the y we're going to have just temperature. We're not going to worry about specifics, and here we're just going to put heating curves. Now this is kind of a basic shape that you're going to find with any element. Pretty much, it could be water, it could be copper, zinc, whatever, and that's why we're not putting specific numbers on the temperature. Basically, it's just the heating curve. So as something heats up in this phase, it will reach this point where it kind of plateaus out, and then it eventually turns and goes into the next state of matter. So these sloped lines are the phases of matter. You're going to have solid at the bottom, then liquid, then gas, and these in the middle are kind of lag phases almost. They're plateaus where the material is changing from one form of matter to the other, and it's not converting all instantly. It's one at a time. So again, I'll just go through these with some colors here. This is going to be solids. Then we have this slope is liquid. And then finally we have gas up here. And basically what we're going to do is we're going to use the different slopes here to figure out which formula we're going to use when we're converting from one state to the other. So first of all, anything that's a sloped line, we're going to use a formula. So let's draw this out here. So if it's any of these, we're going to use the same formula. Q equals M times C times change in T. And then for any of the flatter line, the plateau lines, we're going to use, so we'll just put asterisks on them. They're each going to be different, so asterisk 1, asterisk 2, asterisk 1, asterisk 2. So in this one here, we're going to use the heat of fusion. So Q equals N times the heat of fusion. And then for the second one up here, we're going to have heat of vaporization. So Q is going to equal N times the heat of vaporization. And usually in problems, these will be provided for the specific element that it's referring to. So then we're going to go in through really quick just the states of matter. This might seem really obvious, but sometimes it might help some people to have in there. Obviously, if you're moving from liquid to solid, you're going to be freezing. This way you're going to be melting. But it's cool to kind of see them on the same line, because they could, either one could be happening at the same temperature gap. And then up here you're going to have condensation, and this way you're going to have evaporation. Okay, cool. And that pretty much covers it. The only other one you'll probably occasionally see, I'll put it like way up here. If you go from solid to gas, that's going to be sublimation. And if you go from gas to solid, which is super rare in nature, that's going to be deposition. Sometimes someone will, like a professor will throw in like a single question on one of those just to throw people off or whatever. And then the last thing that I think is really worthwhile to know is this basic trend. If it's moving this way, it's going to be endothermic. If it's moving this way, it's going to be exothermic. It's starting to get kind of cluttered here, obviously, but I think just understanding these concepts, remembering which slope is which state of matter, and then the most important part is remembering these formulas here. So anytime it's on the upward trend or the higher slope, you're going to use Q equals MC change in T, and then these two have their own. Heat of fusion is going to be here, heat of vaporization is going to be up here. All right, cool. So now we're kind of gonna skip ahead. We're gonna start doing some problems, and we'll see where the chart comes in. We'll start with this one. Metal X melts at 550.0 degrees Celsius. Metal X has a specific heat of 0.950 joules per grams Kelvin. And let's see, has a heat of fusion of 9.66 kilojoules per mole. Those are our givens. Now we're going to say calculate the amount of heat needed to melt 125 grams of, of solid metal X, which is originally 25 degrees Celsius. Okay, so there we go. And then we'll say because I didn't say what metal X is, we'll say metal X's molar mass is going to be 22 grams per mole. So it's kind of a wordy problem so far compared to some, but I think that a good way to start is, let's see where we're at. So it said solid metal X, which is originally 25 degrees Celsius. So if we pull out the chart, we know that if it's in the solid phase, just like all of these, we're going to use Q equals MC change in T. So let's just throw in Q, see what we got. Q equals, so we have first M, so the 125 grams. And then we have C, which is going to be, in this case, the 0.950 joules grams per Kelvin. That's our specific heat. And then we have times change in T. Now, change in T is obviously the variance in temperature that you have, what it's going to. So we're going to have 550 minus 25 equals 525 degrees C. It wouldn't matter if that was Fahrenheit or Kelvin yet. It might matter later. But essentially, whether it's Kelvin or Celsius, it's going to be the same because you just add 273 to each of these. The difference will be the same. So we're going to have, for our change in T, plug that in, 125 grams times 0.950 joules times, or over grams times Kelvin. And and 525 Kelvin. And now let's do that calculation out. Let me grab my calculator. Okay, so we're going to have 62343.75 joules. And we can just throw that into kilojoules. That's going to be 62.34 kilojoules. So now what did we basically just do? So where are we at here? We're trying to heat, basically the metal melts at 550, and we're trying to, how much heat is needed to melt it from 125 grams, which is originally 25. So we're trying to go from solid to liquid, and we're going to move this way. So in this case, we'll say the next step will be right here, our asterisk 1, which is what I put it as, N times heat of fusion. So let's see here. We have 125 grams of metal X times, that's going to get confusing, 1 mole of metal X over 22 grams of X, because we know the molar mass is 22 grams per mole. Now we're going to multiply this by our heat of fusion, which is 9.66 kilojoules per mole. So let's see how this works out here. Now, 125 times 1 times 9.66 divided by 22. And we're going to get 54.89 kilojoules. But be careful, because this is not the answer. We've just gone through the flat line here, but we have not progressed technically into it being solid liquid. We got it to start melting essentially, but we're not quite at the point where it's 100% in liquid form, theoretically. So this is not going to be our final answer, but real quick we can double check our units. We've got grams here, grams here. We got moles here, moles here. We're going to be left with just kilojoules, so we can cancel those. And then now what we're going to do is we're going to take, so basically to get it to melt, to bring it to this point where it's melting, we're going to go from, we have this and we have our other number here. We're going to take those two and get the sum of these. So we have 54.89 take 62.34 right here kilojoules, and luckily they're in the same form, in the same units, but if they're not, this is a good time to convert. And then we're just going to add the 54.89 kilojoules, and then from there we'll get 117.23 kilojoules. And that is our critical last step. I think a lot of people probably get problems like this wrong because they get to the final calculation and then they're like, I'm done, I figured it out. You figured out how whatever the melting point is to progress it further from there is what you've figured out before that. You figured out how to get it up into the melting point, but you haven't figured out how to melt it yet. So it's going to be the total heat of both of those. It's always the sum with these problems. So I think it's pretty straightforward in that sense. Now we're going to go into one more problem, which is going to be, I guess, not the most difficult possible problem because of like the units and everything like that, but it's going to be probably the most work you'll have to do, the most steps. This is going to be, as far as a stepwise problem goes, this is going to be the most steps. So you convert a 15-gram block of ice from -10 degrees Celsius to water vapor at 130 degrees Celsius. So that's a huge difference there. How much heat will be needed? So we'll see, what are our givens here? Let's see. 2.092 joules per grams times Kelvin. I think these are actually correct. These are actually the real values. 4.184 joules per grams times Kelvin for water anyway. I have gas. It's going to be 1.841 joule times G times Kel. Times Kelvin, sorry. Heat of fusion is going to be 6.008 kilojoules per mole. Always look out for that. Heat of vaporization is going to be 40.67 kilojoules per mole. Okay, so there's all of our information we're going to need. And just to quickly jump back to that chart we have, in this problem, it's asking us to take a block of ice and turn it into really hot water vapor. So we're going to obviously be down here. We're going to work all the way up here. So we're going to have a minimum of, we're going to have all 5 steps here. So first of all, step 1, we're going to start, we have ice, a solid block of ice, 15 grams of it. So we're just going to start with M times C times change in T. So Q equals, I'm going to write a little bit smaller so I can fit it all. We have 15 grams times, right here we're going to have the 2.092 joules times grams Kelvin, and then we have our temperature difference. So we know for water, it freezes at 0 degrees Celsius. So the temperature difference here is going to be 10 Kelvin, because even though Kelvin doesn't technically go into 0, or I mean it doesn't go into negatives, we know that from -10 to 0, I think a lot of professors anyway will expect you just to know that water freezes at 0 degrees. So then you'll be able to figure that out. 10 degrees, we'll just calculate this, 15 times 2.092 times 10, we're going to get 313.8 joules. And if any of this seems obvious, then feel free to either skip ahead or just pause the video at any time and just try to do out the question and then compare it, or watch it in 2x speed or whatever helps. So we're going from now, this is going to be a crude drawing here, but a block of ice, and we're going to try to get it to basically start melting. And now we're going to have, we're on this line here, we're going to use the heat of fusion formula. So we have Q equals N times heat of fusion. Q equals, we're going to have the 15 grams, because we have the 15 grams of water, melting ice almost, times, whoops, I forgot to, we'll put it like this, 15 grams times 1 mole of H2O over the molar mass of H2O, 18.02 grams. This can get kind of tedious if you write out the whole compound each time, but and then we're just going to multiply that by the heat of fusion over here, 6.008 kilojoules per mole. And then we'll just do that out. 15 times 1 times 6.008 divided by 18. We're going to get 5,001.12 joules. We can worry about that later. 3. Now we're going to have just liquid water. So now that we're in the liquid phase, we can use this next part of the chart, back to our Q equals MC triangle T, we have the Q equals, we still have 15 grams, that's not changing. That looks like 15 grams. And then we're going to multiply that by the specific at liquid, which is 4.184 joules per gram times Kelvin. And then we have our change in T. So here we're trying to go from 0 degrees to 100 degrees. We're going to go 100 Kelvin. What do we got there? We have 15 times 4.184 times 100. 6276 joules. Again, we're gonna worry about that just a little bit at the end. Now we're gonna have supposed to be some bubbles there, some boiling water. It's getting there. Now we have Q equals N times the heat of vaporization. Q equals the moles, which we have, and theoretically, if you calculate it out here, you could use that again, because like I said before, we still have 15 grams. That's not changing. You know, we're just imagining that this is contained, so the water vapor is not flying out of the vessel that you're using to measure H2O. And then we're going to multiply that by the heat of vaporization, which we have up here, 40 point. Actually, yeah, we can do, if we wanted to, we could do 4,670 joules times, oops, what am I doing here? So we have the heat, we have 40.67, that should be kilojoules times grams. Whoops, 40.67 kilojoules per mole, my bad. Oof, that's really messy. Kg per mole. Okay, now we're going to pull that down. We get 3854.05 joules. And then finally on to step 5, our last step. Now we just have water vapor, which is trying to get really warm. So we have, finally we've progressed all the way to this up here. So we're back to using our equation Q equals MC delta T. We're going to do Q equals our 15 grams times 1.841, right there, joules times over grams times Kelvin. Then we have here, we're going from 100 degrees or 100 Kelvin or whatever. That's not our differential. We're going from 100 degrees Celsius technically up to 130, which it asks for in the prompt. But that's going to be a 30 Kelvin difference either way. So we have 15 times 1.841 times 30, and that is going to equal 828.45 joules. Now we're going to obviously get the sum of this to find our final answer, and we have 5 of these. So we're looking at here, 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 and here. We have joules, 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 and joules. So let's just add these up. So we have 313.8 joules. We have 5,001.12 joules. We have 6276. And obviously my sig figs, I'm kind of all over the place, but whatever you need to make it, I think, is your prerogative. It depends on the professor, obviously. 54.05 joules. And then finally we have 828.45 joules. We're going to add that up because that's the heat that it takes from wherever you were here to here, here to here, here to here, here to here, and finally here to here. So you have all 5 of those. And however many steps you have, that's how many calculations you should be finding the sum of. So we're going to end up here with 46273.42 joules. It's kind of a large number. I think my professor usually liked it in kilojoules, but you know, again, figure out what format your professor likes answers in, or maybe they don't care at all. That's going to be our final answer here. So yeah, hopefully everything was on screen this whole time. Hopefully I didn't go too far off. But yeah, basically that's the most amount of steps you'll have to do with one of these problems. And you know, this chart here is something I think it's really worth committing to memory. Just you know, figuring out again if it's going to the right, you're endothermic. If you're going to the left, it's exothermic. And then all those state changes, it's good to know, because if someone says it evaporates, you're going to want to know which direction you're going and between which formula to use, obviously. So yeah, and then again, just if it's solid to gas, that's sublimation. That's like when a block of ice on the road just like evaporates over time instead of melting and then evaporating. That's like sublimation in the real world. And then deposition, I can't think of any real world application of that, but basically when gas turns into a solid, that's deposition. All right, cool. Hopefully this helps someone.